Ladies and gentlemen, welcome to my presentation on mathematicians' greatest mistakes. Yes, they do make them, and even at the highest level. It is not unusual for mathematicians to say words like, "That is what the mathematics tells us, so it must be right." If only that was true. Unfortunately, it isn't. This indicates my mathematics and physics capabilities to pass such comments. In this presentation, a mistake is the difference between what is experimentally observed and what the mathematicians predict. The leading contender with a mistake that can probably never be exceeded is the Big Bang theory for the formation of the universe. Forwarded by mathematicians who call themselves theoretical cosmologists, it goes something like this. In the beginning there was something, or nothing, we don't know yet. It exploded in a big bang, starting space and time. Along the way it broke known physical laws. About 13.8 billion years later, Earth-bound astronomers observed it and measured its properties in reasonable detail. To explain what was observed and measured, theoretical cosmologists decided they needed 24 times the mass and energy that astronomers observed to give the universe a 1 in 10 to the 60 chance of existing. The mathematician's choice is the Big Bang. They will tell you their mathematics is soundly based on Einstein's general relativity theory, so it must be right. A brief glance at his 1916 paper on the foundations of the general theory of relativity soon verifies Einstein's maths were complex. But furthermore, it made predictions that matched observation. How can mere mortals argue against those with mathematical knowledge of such complexity? At that stage, most people put it in the too hard basket. They don't have the mathematical skills to contest the work of those mathematicians, or so they think. To counter that, this presentation is divided into 3 episodes. The first deals with Einstein's gravity and its solutions. The complexities of Einstein's maths seems to make it difficult for mere mortals to question them. To show how easy Einstein's gravity really is, I derived 2 full gravity field equations from his work on gravity. Their derivation and use are nothing more complex than mid-undergraduate mathematics. Even some good high school matriculants could find it easy to solve these simple yet accurate gravity field equations. Yes, gravity is that simple. Einstein made it seem complicated. The second episode deals with all the astronomers' observations that theoretical cosmologists say can only be explained under their expanding universe calculations and theory. It will be shown that under a steady-state universe, they all have simple physical explanations that give a better match with observation. The third episode deals with dark energy and dark matter that mathematicians insist are necessary to explain astronomers' observations. At the end, all we are left with is what the astronomers observe, and that is all that is needed to explain their observations in an infinite steady-state universe. This presentation needs some maths knowledge to understand it. To those who just want to be entertained, they'll find quite a lot as they see the simple mistakes the experts made. To show I'm not cheating, I'm going to display some information written by others, particularly Einstein. Unless otherwise stated, all quotations used will be copied from this book. This page is from his 1905 paper, "Does the inertia of a body depend upon its energy content?" Note the 2 highlighted regions. If a body gives off energy L in the form of radiation, its mass diminishes by L over c squared. If theory corresponds to facts, radiation conveys inertia between emitting and absorbing bodies. Those extracts show Einstein considered that photons had mass. Despite that, later mathematicians treated all photons as massless particles. Ignoring Einstein's work was a big contributor to their greatest mistake. Next we go to his 1911 paper on gravitation and light. In it he applied Newtonian gravity, which he expressed as phi, to photons that he had previously determined had mass. He considered the height difference of photons rising from S1 to S2 against gravity. In a few simple calculations, he showed photon frequency decreased with height as photons lost kinetic energy and gained potential energy. He calculated that photons would be redshifted by 2 times 10 to the minus 6 when they traveled from the sun's surface to Earth. That was already known. And that should have been another wake-up call to all those mathematicians who believed photons were massless. It wasn't. What surprised me was that no one attempted to expand on his 1911 paper, myself in 2021 excluded. Anyone interested can see this United Kingdom Institute of Physics Journal of Physics Communication published at either of these addresses. That expansion involves rearranging terms and early undergraduate calculus. This is about as complex as it gets. It changes Newton's inverse square law to this GR, or gravity redshift term, of GR equals GM over R times 1 plus Z all squared, and that equals GM over R squared e to the alpha over R, where alpha equals 2gm over c squared. It shows that Newtonian distances, Rn, become relativistic distances, Rrel equals Rn times 1 plus z, or Rn times e to the alpha over 2r. Newtonian time becomes relativistic time, Trel equals Tn over 1 plus z. If the wavelength increases, that is, the photons are redshifted, the distance increases. This paper shows that Einstein's space-time distortion to produce gravity was simply photon redshift z. It will be shown later that this matches all known gravity properties. That is not difficult. It could have been done by anyone after 1911. It wasn't. So we have to continue down the path Einstein took. In 1904, Lorentz had already worked out the special relativity corrections for distance and time with constant velocity between an observer and observed. In 1905, Einstein called that correction factor beta, the square root of 1 minus v squared over c squared. He extended the equations to the variations with mass, shown on the top of page 63, and energy, bottom of page 63. As a side issue, it is worth noting his different use of beta. In longitudinal mass, he derived beta cubed. In transverse mass, he derived beta squared. For changes in energy, he just used beta. I have no idea what the difference between longitude and transverse mass were. No wonder his work was confusing. It was soon realized that mass m of an electron at velocity v was given by mv equals m naught divided by beta equals m naught over the square root of 1 minus v squared over c squared, where m naught is the rest mass of the electron. It applies for any other particle. He later realized that the relationship between energy and mass was given by E equals mc squared. Einstein calculated that for electrons. In slide 5, I showed that he indicated photons had mass. Mathematicians assumed that that equation also applied to photons. Therefore, when traveling at the speed of light, they should have infinite mass. They assumed Einstein was wrong and used photons as massless particles in their calculations. A bit of common sense physics, supported by simple maths, shows the corrections only applies to particles. It does not apply to photons. They can only travel at c and will have mass mp equals h nu over c squared. the mathematicians continued their mistake. Michelson and Morley measured the speed of light was constant no matter which direction it was traveling around the sun. Einstein realized that meant there was no absolute reference frame. All measurements were relative to the observer and the observed. He referred to those corrections as special relativity. They applied only to the special situation in which the observer and observed moved at a fixed velocity relative to each other. Einstein was not satisfied with just the special relativity corrections. He wanted to work out the relationship of the general situation in which two bodies were accelerating with respect to each other. That was what he attempted in his 1916 paper on the foundations of the general theory of relativity. He needed to use tensors for that approach, and they were simply vectors in four-dimensional space. But it is worth noting this extract from his foundations paper. It is not my purpose in this discussion to represent the general theory of relativity as a system that is as simple and logical as possible and with the minimum number of axioms. But my main object is to develop this theory in such a way that the reader will feel that the path we have entered upon is psychologically the natural one, and that the underlying assumptions will seem to have the highest possible degree of security. Well, he certainly fulfilled the first part. His paper was not as simple and logical as possible. He did not fulfill the second part. Nobody understood the path he took. If they did, they would never have allowed mathematicians to make their greatest mistake. It is my impression that quotation served its purpose of intimidating readers into thinking he was a brilliant mathematician. Many have tried to understand or follow his mathematics. Despite their pretense, they all failed. So that you will have a better understanding, I'm going to mention a couple of important points and then show you how easy it is to solve his gravity theory. Going through his paper, he started trying to solve the general situation of accelerating bodies, including those traveling in curved paths. Page 122 is his usual style, namely complex maths that are difficult to follow. And that was nothing unusual for Einstein. But as he went through it, he began to get somewhat confused. Although he had previously introduced gravity, Section 8 suggests that he found a way out of that confusion by introducing this standard multidimensional differential equation. He applied it to the four gravity tensors, g, mu, nu. Those g terms are nothing more than the gravity terms in the four dimensions, x, y, and z for space, and t for time. That enabled him to move relatively smoothly from his general relativity theory to its only useful application, namely gravity. After another 17 pages and a mixture of other tensors, he derived his gravitational field equations. The square root of minus g equals 1 means gravity is only attractive. The important feature is the highlighted section below. It must be pointed out there is only a minimum of arbitrariness in the choice of these equations. In that, he was saying equation 47 was an approximation. That also applies to all other forms of his field equations. See, for example, 47a. As every good mathematician will tell you, an exact solution to an approximation is always an approximation to reality. Mathematicians continued their merry way of deriving variations of Einstein's gravity field equations. Here are some examples. The elite claim to be able to solve them and get this answer, the accepted Schwarzschild metric. Being astute mathematicians, they worked out this meant gravity was stronger than Newton's inverse square law. In his 1687 Principia, Newton worked out that if gravity was inverse square, a planet orbiting the Sun would traverse an ellipse in which its perihelion position would always be at the same point, as in A. Kepler had come to the same conclusion earlier. Newton also worked out that if gravity was stronger than inverse square, a planet would orbit a little closer to the Sun and travel a little faster. It would return to its perihelion position a little earlier in each orbit. That would mean its perihelion position would regress against its travel direction, as shown in B. Conversely, if gravity was weaker than inverse square, a planet would orbit a little further away from the Sun and travel at a slower speed. It would take longer to return to its perihelion position, which would precess in its direction of travel. It was known in the late 19th century that Mercury's orbit precessed in its orbital direction by about 43 arcseconds per century. That should have been a wake-up call to those mathematicians who solved his field equations to get this answer. It wasn't. That continued their greatest mistake. Arguments about the validity of Einstein's work or the accuracy of his field equations have been going on for decades. But the easiest way to resolve the argument is to solve Einstein's gravity theory from within his 1916 Foundations paper. Using early undergraduate mathematics will make it easy to understand. To do so, you do not need to know or use his field equations. You can start at any point he used before he derived them. That way, if he made a mistake later on, the solution will still accurately reflect his theory. The best place to start is with this multidimensional differential equation from section 8 of his paper. The two ds squared terms are the same. As mentioned before, the mu and nu terms are x, y, and z for the three space dimensions and t for time. The s term is the four-dimensional space-time coordinate. Filling in all the g, mu, nu terms gives this set. The like terms xx and tt are just those terms multiplied themselves. They become squared and reduced to these equations. That gives this second set of terms. There's nothing complex about that. The next step is to add the d mu and d nu terms. That gives this set of equations. This is a quick reminder from the previous slide that shows the ds squared term. The next step is to realize that when the mass is large enough to generate significant gravity, the gravity at distance r from its center of mass is symmetric. That means the x, y, and z terms are the same. They are different from the t terms. The ds squared term can then be written as shown here. Many mathematicians ignore the a to m terms because they are not needed in the derivation of the solution. So all that is needed to solve for ds squared is to read through Einstein's 1916 Foundations paper and find where he introduces the terms gx and dx as well as gt and dt and insert them into that equation. Einstein used the terms 1, 2, and 3 for the dimensions x, y, and z, and 4 for time. I use x, y, and z for spatial distance to separate it from t as time. Many equations and pages later we come across his term G44, or as he does it, GTT equals 1 minus alpha over r. The alpha term is the accepted 2gm over c squared. But you'll note that he indicates it is an approximation. I mentioned earlier that he admitted his field equations were approximation. This makes two approximations in the term GTT. On the next page, he introduces his G11 equals gx squared equals minus 1 plus alpha over r. It does not include another approximation to his earlier one. The derivation of his dx term equals 1 minus alpha over 2r is given here. Interested parties can pause here to check the accuracy of what is derived. Those steps were introduced to show Einstein used a lot of approximations. They should have been a warning to all those making exact solutions to his field equations that exact solutions to approximations were only ever approximations. It didn't. Mathematicians kept compounding their mistake. That derives the space term. Gravitational time and distance are related through each being the negative inverse of the other. That gives GTT equals 1 over 1 plus alpha over r. Einstein approximated that to G44 equals GTT equals 1 minus alpha over r, as shown here. In the same manner as before, dt becomes 1 plus alpha over 2r, and dt squared equals 1 plus alpha over r. Those approximations are only valid when alpha is much, much less than r. Alpha for the Sun is about 3 kilometers. Mercury's orbital radius is nearly 60 million kilometers. Now, they are valid approximations. I mean, it's sort of equivalent. 1 over 1 minus a millionth approximately equals 1 plus a millionth. We can now insert those terms into the ds squared equation. The x term becomes minus 1 plus alpha over r multiplied by 1 over 1 plus alpha over r equals minus 1. And you can go through the same with the other terms, just that when you get down to the t term, it is 1 over 1 plus alpha over r multiplied by 1 plus alpha over r. So you basically just get these 3 minus 1s and 1 plus 1 term. It is no coincidence that Einstein suggested early in his work that this was the format that would apply. Now, in reality, it tells us nothing except that space response is different from the time response. That brings us to what Einstein considered his greatest thought. An observer with no external reference cannot tell the difference between being accelerated in gravity-free space or being in a gravitational field. The only way of telling the difference is to fix one of them. Fixing the derivatives means fixing a point in space where Newton's g has a fixed value. Fixing them at 1 allows that result to be multiplied by that g value at that point. And so that gives this equation where you have the minus 1 plus alpha over r for the x, y, and z, and 1 over 1 plus alpha over r for time. I mean, these are the Cartesian coordinates x, y, and z, and time t is different. Converting them to spherical or polar coordinates is virtually a lookup table, or details can be found in Shawshield's 1916 paper. That then gives the answer of ds squared equals dt squared over 1 plus alpha over r minus dr squared times 1 plus alpha over r minus r squared d theta squared plus sine squared theta d phi squared. So there you have it. The accurate solution to Einstein's gravity field equations calculated from his paper in a few minutes. Yes, it is that simple. Equally simple is to attach Einstein's radial differential term to Newton's r term in his gravity equations to give Einstein's gravity GE equals gm over r squared times 1 plus alpha over r. The ds squared solutions to Einstein's gravity field equations are not the full gravity equation. They are only the difference between his space-time distortion and Newton's gravity, which is a strength of gravity when there is no space-time distortion. This shows both solutions. The derived solution used the terms Einstein derived. The accepted Schwarzschild solution incorporates the approximations Einstein used. When alpha is much less than r, they give the same answer in most situations. The sole exception is the Schwarzschild metric predicts orbital regression. The derived solution predicts orbital precession. Orbital precession is observed. The big problem came when mathematicians extended the calculations towards r equals alpha. That is what predicts black holes. It is nothing more than mathematicians extending approximations beyond their valid range. Believing those results are accurate is a huge mathematical no, never. Well, it should be. Einstein indicated he used approximations that were only accurate for alpha much less than r. It is left to those who calculated the Schwarzschild solution to explain why they did not recognize and incorporate to get the correct answer. My own impression is that most were carried away with his apparent complexity. It seems they wanted to prove that Einstein was wrong and they were right. Most people would find it difficult to understand, let alone use this solution. As shown in the last slide, all you have to do is attach the differential r squared term to Newton's r squared term to get the full strength of Einstein's gravity at GE equals gm over 1 plus alpha times r squared. It is quite accurate for all values of r greater than about 3 alpha. The same technique can be applied to the Schwarzschild metric. The full gravitational field strength at distance r from the center of mass becomes gs equals gm over 1 minus alpha over r times r squared. It is only valid for r much greater than alpha, and the only exception is that it predicts orbital regression, not precession. Compare those equations to these equations, which the experts say are exact forms of Einstein's gravity field equations. Even if mathematicians could solve them, all they would get is the difference between their interpretation of Einstein's gravity field equations and Newtonian gravity. In the meantime, a lot of students who could solve Newtonian gravity problems could solve these relativistic gravity equations. Einstein indicated Newton's inverse square law of gravity was the first approximation to his gravity field equations. Well, to me, each of these equations seems a sort of variation to Newton's inverse square law. One can only wonder why Einstein did not solve his gravity theory using these two methods mentioned earlier. Was it because he did not understand calculus, so could not expand on his 1911 paper? That could have given him the exact GR equation. Did he not understand how to rearrange the G mu nu terms? That would have given him the GE term as shown above. It would have avoided all possibility of misinterpretations. Or did he realize that if he used either of those techniques, people would realize there was nothing complex in his gravity theory? That would have left him without the aura of a superhuman mathematician. For whatever reason, Einstein's use of excessive and unnecessarily complex maths to derive his field equations gave him an aura as an almost superhuman mathematician. That was his style, so what? So he decorated his maths a lot. It's not his fault that those who tried to prove him wrong, or that they were better than them, could not recognize his superfluous equations, or the simple solutions mentioned above. Nor is it my fault that a century of those who considered themselves the world's best mathematicians or mathematical physicists did not read his 1911 and 1916 papers and recognize the underlying physics and the relatively simple maths associated with his gravity principle. A lot of people find it easier to understand a topic if they can visualize it. This slide shows an image of the four gravity field equations. The horizontal axis is the distance from the center of mass for distances outside its physical radius. It is measured in multiples of the Schwarzschild radius. The vertical axis is the gravitational field strength at that distance. To visualize it, simply use a thought experiment of rotating those curves through 180 degrees around the central vertical axis. As mentioned earlier, the solutions to either the Einstein metric or the Schwarzschild metric given by the appropriate ds squared terms of either is just the difference between the appropriate curve and Newtonian gravity curve. The redshift curve GR was derived from absolute considerations. It goes to the maximum at r equals half alpha, and it has been derived from both an integration and a differentiation. It has a very valid reason for having that shape. So here are examples of 9 different gravity field equations. They can't all be accurate. To finalize this solution to gravity, it is necessary to show which one is accurate. The 5 black on white equations are discarded because, if they can be solved, their solution only provides the difference between Newton's gravity and their solution. That leaves the colored equations. Newton's inverse square law can be discarded because it doesn't explain the observations of Mercury's perihelion, the bending of light rays by the sun, and the observed images at the center of galaxies that are said to be black holes. There are only 2 possibilities. Gravity is either stronger or weaker than Newton's inverse square. Stronger gravity predicts black holes, of which this image is considered an example. Weaker gravity predicts orbital precession, which has been observed. The solution is this redshift metric. It shows that gravity is strongest at r equals half alpha. When particles are attracted by a gravitational field, their greatest velocity will be at their highest gravitational field strength. That is where colliding particles are moving the fastest, and that is where they will emit the most radiation. This redshift gravity equation predicts there will be a torus of radiation having a maximum at r equals half alpha. The so-called black hole image has a similarity to the image predicted from the redshift gravity equation. This redshift metric predicts both orbital precession and the observed images from the galactic center. All factors, including temperature, automatically match. No assumptions are required. Black hole image requires some assumption. This requires none. Black holes are supposed to have a maximum at r equals alpha. These have a maximum at r equals half alpha. Suggestions that at 20,000 or 50 million light years, measurements can be accurate to a factor of 2 are fanciful. The only conclusion is that the redshift gravity, gr equals gm over r squared e to the alpha over r, is the actual gravity equation. It matches all known gravity situations. It has been derived independently by 2 means, one an integral, the other a differential, and it comes associated with a very valid physical reason of why gravity should operate and why it is strongest at alpha over 2. There is no reason why any mathematician or mathematical physicist after 1920 could not have solved for any of those equations. Had they done so, they would never have allowed their calculations to go so badly wrong. After all of that, what is Einstein's gravity? It is a mathematical theory, as he said it was. It is founded on Newton's gravity theory and his calculations that photon had mass. His 1911 paper allowed him to visualize how gravity worked. He tried to solve the general relativity situation of bodies accelerating with respect to each other. For that he needed tensors. It got too complex, so he reverted to a study of gravity, its only useful application. Einstein used his visualization as a guide to make his way through his gravity equations. That enabled him to say his gravity theory originated from his general relativity work. It derived the correct answer for the bending of light rays by the sun at the end of all his complex maths. He introduced the idea that gravity was caused by mass distorting space-time. He never indicated what space-time or its distortion were physically. His complex field equations are shown in these black-on-white equations. That led others to try to solve them. They did not understand the physics that underpinned them. If they did, they would have solved and got the GE equation. Or if they had simply integrated Einstein's 1911 paper on gravitation and light, they would have derived this exact equation. None did. That is why they drifted off to make such a huge mathematical mistake. The next episode shows how that drift led to their huge mistake.